In this video, I'm going to show how to run a simple regression using the solo growth model as an example, where we're going to relate real GDP to the investment rate. We're not going to worry about issues such as stationarity or autocorrelation. We're just going to look at how to run a simple model in Stata and how to interpret a number of important factors. So, using a do file, I've already set my working directory and loaded in my data and opened a log file. So we can do log using. What I'm going to do then subsequently is generate the log of the variables. So we're going to get the natural logarithm of the real GDP and the investment rate, where real GDP is or GDP and I is the investment rate. If we run these, what we can see is we're generating two new additional variables for inclusion, in our data set. The labeling the variable command simply just generates new labels on the variables. So these labels we can see appearing side by side here. And essentially what these labels actually do is just appear in any graphs that we do. So rather than having ln read GDP, which is somewhat idiosyncratic to our dataset, instead log of real GDP will appear on the x or y axis. Now, we can draw scatter diagrams using the scatter command, which are very straightforward to actually implement. And when we actually run our scatter diagram, what we can see is we can see the relationship between our actual variables. So we can see log of investment rate and log of real GDP. What we can also do then is using the 2a command, again run a scatter diagram, but have a fit of a linear fit model overlaid over this. So we can have our straight linear fit model. And this is our line of best fit or regression line. What we can see again is this positive relationship with the linear fit line being upward sloping from left to right, indicating a positive relationship. Now, what we're mainly interested in this example is what are the key elements to come out of a regression model where we run these two variables. So where we run the effect of the investment rate on real GDP. So if we run this model, what we can actually see here is a summary of our regression output. Now, a number of points can be noted here. First of which is number of observations is 60. This means we've run our analysis on 60 years of data. In our case, the data is for Ireland from 1950 until 2010. So 1950 to 2010, giving us 60 observations. What we also have is probability for our f-test, probability for our t-tests, coefficients for our t-tests, and our r-squared. In terms of the order we want to interpret these, we're going to start with our f-test, progress to the r-squared, then to the t-test of individual coefficients, and then on to the coefficients themselves. Now, with our f-test, we can see here the actual f statistic, and we can use an f-table to look at this and check the significance of our overall regression model. But of interest to us in this particular example is the p-value for our f-test. Now, the null hypothesis of the f-test is that the r-squared equals 0. Essentially that our model is no good. It explains none of the variation in our dependent variable. The alternative hypothesis is that the r-squared does not equal 0, i.e. that our model has explanatory power. With a p-value, when we're doing our f-test using these, ideally what we want to see is the probability greater than f being less than 0.1, 0.05, or 0.01. These corresponding to the 90, 95, and 99% significance levels respectively. As our p-value for f is 0.000, i.e. essentially 0, what this means is that as it's less than each value, 0.1, 0.05, 0.01, we can say that our variable is statistically significant at all these significant levels. So our model is statistically significant at all these levels. Because the 99% is the strongest, being 99% confident in something is stronger than being 90% or 95% confident in it, we're going to say we're 99% confident that we can reject the null hypothesis, and the null hypothesis is that the r-squared equals 0. So we're rejecting that, and we're going to conclude the alternative hypothesis, that the r-squared does not equal 0. Basically, this means our regression model has some explanatory power. So, our f-test has shown that our regression model has explanatory power. It is a good regression model to work with. If the p-value here had been above 0.1, we would not work with this regression. The next thing to consider is our r-squared. What we can see with the r-squared value is that we've got a value of 0.3455. The r-squared takes a value between 0 and 1 and is known as the coefficient of determination. The closer it is to 1, the better the model. The closer it is to 0, the worse the model. We can use the r-squared to say here, in our case, that 34.55% of the variation in real GDP is explained by investment. So 34.55%. That leaves us with about 65% which is not explained, okay, or error in our model. So the r-squared here is acceptable, it's quite okay. Following from the r-squared, we interpret the t-values, okay? And what we're going to be specifically interested in are the p-values for our t-tests, all right? Now with these, we interpret them in the same way as we do for an f-test. Ideally, what we want to see is a t-value being less than 0.1. So we want to have our p-values for t being less than 0.1. In this case, we can see that for both of our coefficients, ln I, the log of investment rate, and our constant, the p-value is less than 0.1, 0.05, and 0.01, as both p-values are actually 0. The null hypothesis in the case of a t-test is that the variable equals 0, or that the coefficient of the variable equals 0. So essentially that the coefficient for the log of the investment rate is equal to 0, and that the constant is equal to 0. It's possible to reject the null hypothesis in one case and not reject it for another with our p-values for the t-tests. We will have the same number of t-tests as we have independent variables in the model. So it's possible to have 7, 8 or above t-tests in a model. What we can see in this case is we're rejecting the null hypothesis in both cases, as they are 0. This means that investment has a significant effect on real GDP. Okay, so we are confident at the 99% level that investment does not equal 0 and that it has a significant effect on real GDP. Having interpreted the t-tests, we now move on to looking at the actual coefficients. And in this case, the coefficient for investment is 1.6, and the coefficient for our constant is 4.65. So these essentially show the nature of the relationship between our variables. When investment is 0, the log of real GDP is 4.65. 1.6 is a positive number. This shows that investment and real GDP are positively correlated with each other. And what we can see is that a 1 unit increase in investment causes a 1.6 increase in real GDP. So we interpret our coefficients as such. So to recap, the order in which we go through this analysis is we look at the p-value for our f-test first, we look at our r-squared value second, we then look at our two t-tests, bearing in mind that the number of t-tests will increase as more variables are increased, and then we look at the coefficients. This is the order in which one should go about interpreting your regression output.